Let's continue looking at the idea of modeling the interaction of two populations. We'll look at a couple different example problems in this video. So first, let's look at, instead of populations of species, let's look at the values of two businesses. When we're talking about species interacting with each other, it does have a common idea to businesses interacting with each other. Sometimes businesses can help each other out as like a symbiotic relationship. Sometimes businesses can hurt each other because there's competition over customers. And sometimes there's a predator-prey situation. You may think like a big box chain like Walmart might hurt a mom and pop shop on Main Street or something. There's lots of similar kind of ideas that could go with this. So here we're thinking of the values of two businesses are given by X and Y. This is how well both those businesses are doing. And we're going to describe what each of the following systems of differential equations would represent in terms of the valuation of each company. So this is, we're going to try to determine, is there a food competition idea, a symbiosis idea, a predator-prey thing happening, or maybe is there something else kind of going on? To look at this, we are going to be focusing on the signs of the terms in each differential equation. So first, let's look at the first thing here, A. This is the simplistic idea here that the derivative of x, the change in x, has only something to do with x. It doesn't have anything to do with y. And similarly, the change in y has only something to do with y. So this is, these two companies don't affect each other. So these two businesses do not affect each other. We can say that in the first one, business X, we can say that the value of this business decreases over time. It's going to decrease at a rate proportional to its population. It's going to decrease because of that negative constant. And same thing with the other business. So the value of business Y decreases over time. I should say this is business X, so the first one. Okay, but in general, those two businesses don't have anything to do with each other because there's not a Y or an X in the other differential equation. This is like our differential equations we've dealt with so far in this chapter. All right, in the second one, we have dx dt equals y minus x, and dy dt equals x minus y. So these are kind of the same sort of idea here, but for the first one, we can see that because of the negative x and because of the negative y here in the second, that both companies decrease over time without influence from the other. And the y, the positive y and the positive x here are saying kind of an odd thing, that's saying that the better y, the company Y does, means the better that X does. There's some kind of symbiosis relationship happening here. So we can say that the valuation of company X increases if the valuation of if that of company Y increases. And vice versa. So this is kind of like symbiosis, but there's something a little bit different going on here. So this is just saying, just if company X increases, then company Y can increase as well. There's something very simplistic about it, rather than thinking about the number of encounters, where they're kind of looking at each other. So this is symbiosis-like but not quite symbiosis. And note that we are not really going to deal with differential equations of this form. So we should make a little note here. Note, we will not see equations like this very much. This is just to give an idea maybe what that would represent. So it's the next two equations that we are going to see in this section and that we really want to focus on the most. So here, and this looks like our equations we built in the lecture video, we have dx dt has a positive x here, and dy dt has a positive y. So that says that both companies would grow without influence from the other. So if they were just left alone and there wasn't a second company involved, both those businesses would increase their value. However, because of this negative x and negative xy, this is the idea of a food competition kind of thing. And we are saying, in this case, this might be like customer competition. So when both these companies do better, there's an effort for both of these companies to drive in customers, but somehow there's a limited amount of customers, there's a limited amount of resource. So when both companies start doing better, it actually decreases the amount that it can grow over time to a point that it might actually start decreasing the valuation depending on the constants that we're looking at. So this is what, like we did in the lecture video, this is a food competition or a customer competition kind of idea. And in the last differential equation, we have the same idea as down here. Both companies would grow without the influence from the other. That's from the positive x and positive y. But here, because of the positive xy, we have this idea of symbiosis. That both increase their valuation if the other company does well. And this happens a lot in the business world. Sometimes it helps to have even a similar kind of business near you. It drives the whole idea. Or maybe these are two completely different kinds of businesses and they both help each other out. So for instance, when you have a large sporting arena, that has a positive influence over the restaurants near that area because it drives in customers and the other one drives in customers. If you have good restaurants near that sporting arena, that might have a small positive influence on the sporting arena itself. So sometimes different kinds of businesses can often have a symbiotic relationship with each other. All right, so this I think is the main point of this chapter is, can you look at these differential equations and can you try to understand what interactions these populations are having? In this last example in this video, we're just going to look at just one specific example and think about some questions we could ask about it. So here we're going to have the population of two alien species, A and B, is symbiotic. That means that they help each other out. When one population increases, the other one benefits from that, and vice versa. So without the presence of B, the population of A grows at a rate of 2% per year. Without the presence of A, the population of B decreases at a rate of 0.5% per year. Now we're going to say the number of encounters of the species grows at a rate of 3% proportional to the product of the population. So what that means, encounters is going to be the thing that benefits both of these populations. We can think about a bee pollinating a flower or whatever it's going to be. So here we're going to have a system of differential equations, and that just means we're going to find dA dt, and we're going to find dB dt, the derivatives of both alien populations. So first, we have the population of A grows at a rate of 2% per year if there's no influence from B at all. So this is what we've done earlier in this chapter. This is going to say that we have a 0.02A term in our differential equation. 0.02 is corresponding to that 2%. And for B is going to decrease at a rate of 0.5% per year. So we're going to have a negative 0.005B. Note that 0.5%, we move the decimal point over twice, that's 0.005. And it's going to decrease, so we have that negative. So without A, B doesn't do very well, it decreases. Without B, A can still increase, but it will increase more because of that symbiotic relationship. So now let's look at that symbiotic relationship. This species grows at a rate of 3% proportional to the product of the populations. So that is going to be a 0.03 times the product of the populations. And here are our two differential equations representing the populations of both these species. And these are more complicated than what we had earlier in this chapter because they both depend on each other. There's A's and B's in both of these differential equations. So now we could ask questions like we've done earlier in this chapter. We're going to pick just one right here. And we could say, given this differential equation, if we look at a specific point when the population of A is 2,000 and the population of B is 1,000, are the populations of A and B increasing or decreasing? And we're going to say that A and B are in thousands. So we're going to say here that A is equal to 2 and B is equal to 1. So if we want to find out if the populations of A and B are increasing or decreasing, we want to find the signs of the derivative of both. So since we have a formula for that, we can look at individually dA dt, which is going to be 0.02 times A, which is going to be 2, plus 0.032 times 1, and this will give us a 0.04 plus 0.06 will give us a 0.1. So this is positive. So this means that the population of A is increasing at this time, or at this level. And in fact, we can maybe see that from the beginning. The population of A is always going to increase because there's no negative side effects in this example, what we have here. For B, that's not so obvious because if the number of encounters isn't big enough, then we're actually going to be decreasing. We have a negative term, so there's a population of decreasing here, or a possibility of decreasing. Either way, we look at 0.005, negative 0.005 times B, which is 1, plus 0.032 times 1. This is negative 0.005 plus 0.06, which will give us positive 0.55, which is going to be greater than 0. Sorry, I should say 0.055, which is greater than 0. So this is also increasing. Given a different level of A or B that we plug into that second derivative, we may find that it would be negative, so therefore it would be decreasing at that time. We could also ask questions about what that value means. So what does this value of 0.1 mean in dA dt? That's saying if we go 1 unit of time, in this case we're looking at years, so if we increase 1 year, we should expect the population of A to increase by 0.1 unit. In this case, if the units is 1,000, we think it's going to be 0.1 of 1,000, so this is going to be increased by 100 units, 100 species. But we could ask similar questions in that vein, and we're going to have some example problems that look at similar kind of ideas. Lastly, we're going to look at a differential equation that has to deal with both those, that is dA dB. Algebraically, this is going to be very easy to do. So dA dB is just going to be the derivative of A over the derivative of B. And that's going to be 0.02A plus 0.03AB over negative 0.005B plus 0.03AB. So that's very easy to do algebraically, and there's lots that we could do with this differential equation, but note that a lot of what we can do has to deal with the slope fields and the phase planes we're not going to talk about in this chapter, so we're just going to talk just very generally about what this represents, this dA dB. This is somehow giving us an idea of how much is the population of A going to increase or decrease just in terms of the population of B. So it's just focusing in on one of those populations just in terms of the other. It's a little more simplistic. It's like we're getting rid of one of the variables, that in terms of T. So we can say that as B increases or decreases, what happens to the population of A, and vice versa. Not so much over time, but again, just in terms of that. We're not going to ask a lot of questions about that differential equation, but it's nice to know how we can find that. And there is stuff that we could do if we had more time in this chapter.